Linear regression is one of the simplest yet most powerful algorithms in machine learning. It's a fundamental concept used to model the relationship between variables. Let's break it down. At its core, linear regression tries to draw the best straight line through a set of data points to predict an output variable based on one or more input variables. When we say linear, we mean the relationship between the input and output is modeled as a straight line. There are two main types of linear regression. Simple linear regression, where we use one input feature to predict the output, and multiple linear regression, where we use two or more input features. Let's start with simple linear regression. Imagine you're trying to predict a person's weight based on their height. The algorithm will try to fit a straight line that best represents the relationship between height and weight. The equation of a straight line is y equals x plus b, where y is the predicted value, m is the slope of the line, x is the input variable, and b is the y-intercept. The goal of linear regression is to find the best values for m and b that minimize the error between the predicted values and actual values. This is done using a method called least squares. It minimizes the sum of the squared differences between the actual data points and the line. The error is calculated using a loss function called mean squared error, MSE. The model adjusts its parameters to reduce the MSE using optimization techniques like gradient descent. Gradient descent is an algorithm that updates model parameters step by step to reach the minimum loss. It's like rolling a ball downhill to find the lowest point. Now let's talk about multiple linear regression. When more than one independent variable is involved, the model fits a multidimensional plane instead of a line. For example, predicting house prices using features like square footage, number of bedrooms, age of the house, and location. In this case, the equation becomes y equals b0 plus by1 plus bx2 plus bnxn. The model still uses the same logic, minimize the error between predictions and actual values. For linear regression to work effectively, several assumptions must be met. Linearity. The relationship between inputs and output is linear. Independence. The input variables are independent of each other. Homoscedasticity. Constant variance of error terms, and normal distribution of errors. Residuals should be normally distributed. If these assumptions are violated, the model might give biased or inaccurate results. Linear regression is widely used in forecasting sales or trends, predicting prices, e.g. housing or stock prices, risk assessment in insurance, health outcomes prediction, and student performance estimation. Despite its simplicity, linear regression is a baseline model used to understand relationships and validate more complex models later. It's also highly interpretable, meaning you can understand exactly how each input affects the output. Pros of linear regression include being easy to implement and understand, requiring little computational power, and being a good starting point for predictive modeling. Cons include being limited to linear relationships, being sensitive to outliers, and can underperform when data is nonlinear or multicollinear. Today, linear regression remains a building block in machine learning education and real-world use cases. It's often used as a first model to try and a benchmark to compare others against. If this helped you understand linear regression, don't forget to like, share, and comment below. Let us know which machine learning topic you'd like next.